Today we're going to continue learning about log functions. The first thing we're looking at is the inverse, or finding the inverse. So as we've previously talked about, log functions are the inverse of exponential functions. Just like addition is the inverse of subtraction, and multiplication is the inverse of division. So to find the inverse of a logarithm, you need to follow these 4 steps. You need to start by switching the roles of x and y. So you literally switch your variable x, change it to a y, and you change your variable y to an x. You isolate the log expression on one side, so pick a side, either the left or the right of the equation. You keep the log, the base, and the argument by itself. So notice over here I just made a little note. Step 3 is to convert or transform the log equation into its equivalent exponential equation. And then you solve for y. So this little note off to the side, you need to keep the log, the base, the argument together. If I gave you an example of what I mean by this, if we have log base 2 of x plus 3 minus 6, this step is telling us that we have to keep the log, the base, and this argument together. The value of plus 6 can move wherever, minus 6, that can move wherever we want it to. Just make sure you keep that highlighted section together. For the first example, we have y is equal to log base 3 of x. Following the directions above, the first step is to switch your x and y variables. So I'm going to rewrite this as x equals log base 3 of y. The second step and the directions that we have right here say to isolate the log expression, meaning to isolate the log, the base, the argument. Well, that's already done here. We don't have anything that's being added or subtracted, so it's already by itself. Next, we need to convert or transform the log equation to its equivalent exponential equation. So we need to either use the loop method or convert this however you're converting to exponential form, which is going to be y equals 3 to the power of x. And the last step would be to isolate y. In this case, y is already isolated. This is a basic one. It's as basic as we'll see them. So this here is our inverse. Number 2 starts to get a little bit more complex. Remember that you cannot separate the log, the base, or the argument, so this has to stay together until it's an exponential form. Step 1 for finding the inverse is to switch your x and y variables. X is equal to log base 2 of y plus 3. Then you have to isolate the log, the base, and the argument, which is actually already done. Remember, we can't separate that set of parentheses. So the next step is to convert to exponential form. And again, you do that however you're comfortable doing it, either the loop method or memorizing the order. But we're going to end up with y plus 3 is equal to is equal to 2 raised to the power of x. At this point, we want to isolate the value of y. That means we need to subtract 3 from both sides. And our final answer is 2x, 2 to the power of x, minus 3. and this here is your inverse of your original function. Number 3 is log base 4 of x plus 2. So our log, base, and argument have to stay together. This term right here is fair game to move around with the function. To start off with, I'm going to switch this to x equals log base 4 of x of y plus 2. So I switched my x and y variables. Remember, this right here can move around, and it actually has to. We need to subtract it from each side. We need to isolate just the log, the base, and the argument. This gives us x minus 2 is equal to log base 4 of y. Once you're at this step, you need to convert to exponential form. So just be careful because this whole piece right here is going to be your exponent. When you draw the loop around your function, if you're doing that method, this whole thing is going to replace or go in place of your exponent. So at this point, it looks like y is equal to 4 raised to the power of x minus 2. Our last step would be to solve for y, but y is already by itself, so therefore this is your final answer. And lastly, number 4. Number 4 has everything to it. So it has an argument that's in parentheses that needs to stay together, and it also has a single term that we can move around the function. Step 1 is to switch x and y. X is equal to log base 5 of 2 times y minus 1 and then minus 7. Step 2 is to isolate the log. This gives us x plus 7 is equal to log base 5 of 2y minus 1. After we have the log, the base, and the argument, this is the argument, I keep using that word, hopefully you know what I'm talking about. Then we can convert to exponential form. 2y minus 1 is equal to 5 raised to the power of x plus 7. So this whole piece is your solution. This right here is your exponent. Now you need to isolate y. So in order to do that, I'm going to add 1 to both sides. Be careful what you're adding your value of 1 to. This is 5 raised to the power of x plus 7, and then it's plus 1 after that. Plus 1 is a whole number. It is not part of your exponent. Then I have to divide both sides by 2, giving me y equals a numerator of 5 raised to the power of x plus 7 plus 1 as a constant divided by 2. This is your final inverse. Okay, next we need to talk about a couple properties of logarithms. We're just going to touch on these lightly. When you go to pre-calc, you'll see that we go a lot further into these properties. So the first property that we're going to look at is the zero exponent rule. And that's important because, well, you've actually already seen this happen once, but if you have a log with a base, any base, and then an argument of 1, your solution will always be 0. So anytime that argument is 1, your solution is equal to 0. The product property says that if you have log base b of x times y, you can expand this to log base b of x plus log base b of y. So this is saying that if you have multiplication, you can expand with addition. There's a couple things you need to notice. The log and the base in the original function is going to be the log and the base in each expression. It's very common for students to forget to write one of those. Make sure you put it in both places. Also, you have a value of x, that's going to be the first part of your expression, and then your value of y is your second expression. Next is the quotient property. Quotient pairs division with subtraction. So if we have log base b of x over y, we can expand this to log base b of x minus log base b of y. So if we have division, we can expand with subtraction. And same thing goes, whatever your log and your base is, you need to make sure that ends up in both of your expressions. Whatever your numerator is, in this case it's x, that's going to be your first expression, and your denominator becomes your second expression. Lastly, we have the power property. The power property says if we have log base b of x raised to the power of p, this p being an exponent, we can rewrite the exponent as a multiplier, becomes p times log base b of x. So if you have an exponent, I spelled that wrong, exponent, then you rewrite that exponent in front of your expression as a multiplier. Okay, so the next section of examples, we are expanding the logarithms. So you have to use all of these properties above, these that we just went over, and you need to break apart your log as much as you can. Now, with problems like these, there is no specific order to using the properties above. You just have to be able to apply them as necessary. So you have to break them down in steps. If we start with the first one, we have log base 4 of 7 times x. Of course, this right here is multiplication. So if we're expanding this, this is going to be the product property, and the product property tells us to expand with addition. So I'm going to separate this as log base 4 of 7 plus log base 4 of x. This is my expanded function. Make sure you put log base 4 with both of your expressions. And why I keep emphasizing that is because I see this a lot. I see students do log base 4 of 7 plus x. This is completely wrong. You need to make sure you have that log in the base with each of your expressions. Number 2 is log base 2 of d over x cubed. So we have a couple of things happening. First thing I notice is that we have division. And the second thing right here is that we have the exponent, which is going to be the power property. So if you're wondering which order to go in, you have to look at, okay, well, the exponent only applies to the denominator, so I only need to work with that specific denominator. But the division is applied to the entire problem. So I'm going to start with the quotient property, and I'm going to break this down to log base 2 of d minus log base 2 of x cubed. It's the only thing I can do at this step because, again, this exponent is only applied to that value of x. It is not applied to the numerator as well. So we started with the quotient property. Then we're going to recognize that we have an exponent only on that second expression. So our first expression remains the same, log base 2 of d, minus, that exponent is going to go in front as 3 times log base 2 of x. And this is using the power property. The power property usually comes last. There are a couple cases where it doesn't, but most of the time the power property is the last step you'll do with expanding. And the last example set is working the opposite way, so it's condensing the logarithms, meaning you have them already expanded and now you need to bring them back together to one single logarithm. When you do this, you need to make sure your arguments, well, the logarithm and the base are the same. So number one is log, it's technically base 10, but we don't see that. So hopefully everyone remembers base 10. Log base 10 of 6 minus log base 10 of 2. Right here we see subtraction. Recall that subtraction is paired with the quotient property. It's paired with division. So I can rewrite this as log base 10 of 6 over 2. And then 6 over 2 can also be simplified. I can write this as log base 10 of 3. So I started with an expression that was already expanded, and I brought that back to one single log. If you want to write base 10 in your final answer, you can. You just don't have to because it is the common log. Number 2, we have some coefficients in front. So when you're expanding, which was the last example set, you do the power property last. But when you're condensing, like this one right here, you need to do the power property first. You need to get rid of those multipliers. So I'm going to rewrite this as log base 3 of x raised to the power of 4 plus log base 3 of y raised to the power of 2. I also need to make sure, are my bases the same? And in this case, yes, they are. You can only condense if your bases are identical. Because I have addition right here, addition pairs with multiplication, which forms the product property. The product property tells us that we can rewrite this as log base 3 x raised to the power of 4 times y squared. So you separate, or you condense the addition with multiplication. So while we started with 2 logarithms or an expanded log, we condensed this to one single logarithm. Okay, please let me know if you have any questions.